I hope my screen is visible to you. My audio and video, my audio is clear to you.
Everything is perfect.
Okay. So once again, very good day to you, my dear students. We are uh, getting on to data structures, which is our third subject. This is Introduction to Data Structures, and this is especially for you, my dear students and young researchers. Of course, you know me. I'm Dr. Professor Christo Ananth. You can reach me at dr.christoananth@gmail.com. So before beginning the session, I request everybody to please pray for a while to keep us healthy all these days, to keep us happy all these days. And as for me, I thank God for giving me this golden opportunity to deliver this useful session, to share my knowledge among my fellow national, international participants, students, and young researchers. So today's class will have a short introduction about data structures, and then we'll discuss how we try to design an algorithm, how we uh, categorize this algorithm according to the program code that we try to develop in order to computer to understand. And then we'll discuss about pseudocode, about the various specifications, space complexity. We'll discuss something about time complexity as well. And then we'll discuss about the memory usage while execution, the various different approach to design an algorithm, data structures, the various abstract data types, how you design patterns, and so on. And we'll discuss something about the common and the most popularly used data structures. What are the basic operations that are performed in the task? And then we'll discuss something about the binary tree. We'll elaborate more about the binary search tree, the heap, the hashing data structure, and finally we are going to end with the matrix and the trie. Okay, so of course I have already posted the element works in the Google Classroom, so those students who have already joined in the Google Classroom will get to know the syllabus, the materials, and the element work as well. So please do complete on time. As I told you, 5 element works and 1 project work. Okay. So of course we'll have at regular intervals some short videos to discuss the and test the knowledge in our topics. So this is a short introduction to data structures. So data structure, if you define it, it's actually a way that you try to categorize it, the way you try to, the organizing data so that it can be used effectively. You can test it, you can test for performance, you can evaluate it, and you can get the desired result. But the background objective is that you have to reduce the space, you have to reduce the time complexity of different tasks, because each of the tasks might take different time interval. Each of the tasks would require operations that might require more space. So you have to reduce the space as well as the time complexity. And for a good data structure, it allows you to perform variety of critical operations. So an efficient data structure would use less memory space and faster execution time to perform these data structures. When you take in the case of the applications, you have data structures being used in OS, operating system, graphics, computer design, and then simulation experiments as well. So this is the classification of data structures. We have the built-in data structure and the user-defined data structure. Within the built-in data structure, we have integer, we have float, we have character, and then we have pointer. But user-defined data structure, what we try to define, we have arrays, lists, and files. So here within the list, we have linear list as well as non-linear list. And with the case of linear list, we have stacks and then queues. Okay, we have like first in, first out, last in, first out. Okay, let us take in the case of a bottle. Okay, you try to fill the bottle with maybe biscuits. Let us take in this. Okay, maybe the first biscuit which is fed in is the last biscuit to come out. Okay, so this is how you tend to work in with the first in, first out, and last in, first out technique. Okay, and then we have trees, we have graphs as well for the non-linear lists. So in the lower classes, maybe in your school days, you would have studied about algorithms, you would have studied about flowcharts, and you have any idea about algorithm. You write something like a complex program. You write a simple algorithm in steps. Start the program, get the inputs, process the input, and finally you get the output. Okay, or maybe print the output. So this is algorithm, which is a finite sequence of instructions, each of which has a clear meaning, which means it can be performed with finite amount of effort in a very less amount of time interval. But when you try to write algorithm, normally you write in simple English, okay, that is understood by the human beings. But the thing is that you should make sure that the computer, what you are trying to feed, has to understand whatever you write. So the in computer, it should be written in a language that should be understood, and it should be executed as well. So the language which you feed into the computer should be a formal language. Okay, and computers, as you know, are very flexible compared to the human mind, and they can understand the programs according to the logic that we are trying to feed. So here, when you try to write an algorithm, we tend to omit all the programming details, but you concentrate on the design of the algorithm, the motive, the actual logic behind the program. So here, when you try to write the algorithms, when you try to build a code for your program, normally there are two programmings that you have to take into consideration. Okay, so this is imperative programming and then declarative programming. Whenever you discuss about several algorithms, normally we tend to concentrate only on the theoretical part alone, but we tend to forget the practical part. But the thing is that the algorithm should take into consideration both the theoretical concept as well as the practical concepts as well. Also, when you have to write a very large program, you have to break it into simple steps. Okay, subtasks as well, so that you tend to test one subpart of that algorithm, and then you tend to get a an intermediate results. Okay, right. So with the case of imperative programming, it is nothing but computation in terms of instructions, which is going to change the program state or maybe the data state. Whereas in the case of the declarative programming, it is going to specify what the program should achieve without describing how to do it. So we are going to focus on the objective, the final result, but how we have to do it, nobody knows with the case of declarative programming. Next comes pseudocode. Pseudocode, actually it is pseudo means false. Okay, so it's a false code. So let us take in the case we have three people and two people are connected and one of them is a third person. Okay, so we tend to communicate with each other using the pseudocode. Okay, but the third party doesn't understand. Okay, so you should make it understandable to, in order to make it understandable to the third person, we have to write it in a common language where the third person, second person, and first person can also understand. Okay, so normally when you try to write algorithms, it should be written in plain English that a human being can easily understand. But for a computer scientist, generally for him or maybe for her, it should be written in a language that should be understandable by both the computer as well as the human beings. Okay, so this is pseudocode. We tend to take different forms out of the pseudocode. Okay, so maybe if you take in the case of a C language or maybe Java language. Okay, so you tend to write it in program codes as well. You tend to execute it, but when you understand the logic of the program, it should be written somewhere between the human readable form as well as the computer understandable. there are fundamental questions about algorithms. Normally, we don't tend to ask these questions, but you should ask these questions. Okay. So whenever you are writing some algorithm, you should ask, what is it supposed to do, or what is the objective, what is the goal, okay, that an algorithm does, or does it really do what it is supposed to do. Okay, maybe we are doing something, but whether this is the real objective, okay, you should ask. And how efficiently does it do? Okay, so how proficiently it is going to do all the tasks. So that also you should ask it to the algorithms that you are trying to design. Okay. So whenever you take in consideration of the algorithms, okay, so we have some key concepts called specification, verification, and performance analysis. Specification, verification, and performance analysis. For example, specification means it is nothing but the design considerations. It is nothing but the tools, okay, the hardware, software, what we are trying to need in order to get the output. So that is specifications. And then verification, you are going to test it, you are going to test the analysis, okay, you are going to verify the subparts, okay, only if you verify the subparts you will get the main output. So this is verification. And finally, performance analysis. Performance analysis is testing its behavior, okay, with regards to several inputs, how your particular output is performing with comparison to the existing algorithms. So this is all about performance analysis. So you can rather say it is all about the problem that you are trying to evaluate to. So if your problem is very simple, which means that the specification, verification, and performance analysis is also simple. But when you take into consideration about a complex problem, then it differs. You have to break it into subparts and you have to evaluate accordingly. So we'll discuss something about specifications. So we have some very detailed analytics about the problem that the algorithm is intended to solve, and it should be presented in an abstract fashion. Okay, so it should be presentable to the authors or maybe readers who try to understand it. Okay, so here in the specifications we have inputs, we have outputs, and there should be a relationship between the input and the output. So there is no compulsion that the specification has to be complete, but it can be incomplete even, but there should be proper relationship between the input and the output. Okay. So it's very easy to see that a particular algorithm will always work, will satisfy its specification, and for complicated specifications or algorithm, the algorithm satisfies its specification, now it can satisfy or it cannot satisfy. And then we have like testing. So which means that testing means we test the algorithm for its for output, and if you take in the case of input, it can be one, it can be two, it can be many, it can be infinite. Okay, so more than just testing, you make sure that the algorithm satisfies its specifications, which means that we need correctness proofs. So if you are able to do that, okay, it is understood indirectly that it is being tested. Okay. So we'll discuss the proofs, we'll discuss invariants, okay, we'll discuss it in an informal manner as well. But whenever you are going to test it, you should take into consideration on the the several algorithms and the data structures that you are trying to design, and you get the desired result. So this is testing and efficiency. So you're going to test the efficiency for how the algorithm acts, how you feed in the resources, how fast your system is going to produce the required result. Okay, so as I told you in the beginning of the class, the data structure is all about reducing the time complexity as well as the space complexity. So how far you are reducing the computer memory, how fast it is going to execute, really matters. Okay, so it all depends on the problem size. Okay, problem dependent as well. So if the problem size is very less, okay, which means that the data representation is also less and the algorithm details is also less. It's very important that you have to come up with efficient data structures in order to design a problem and you get the required result. So this is all about space complexity. So you can say that it is the amount of memory space which is required by the algorithm during the time of the execution. Okay. So it can be for a single user system or it can be for several user systems as well, where the memory is actually limited. Okay. So when you take into consideration the space complexity, we have three spaces. Okay, one is instruction space, second is data space, and the third one is environment space. If you take in the case of instruction space, it is the space which is required to store the executable version of the program. Okay, so you tend to allocate a space for the running of the program. Okay, but this space is actually limited. It is actually fixed, but it varies depending on the number of the lines of the code in the program. Okay, so depending on the lines, the space differs. And then you have the data space. So data space means something related to data. So which means a space for constants, a space for variables. A space for variable means it can be temporary variable or it can be permanent variable as well. And then you have an environment space. It is the space which is required to store the environment related information. For example, if there is some task which is performing and then the task gets stopped once in a while. Okay, so you need environment characters. Is it because of the climatic changes? Is it because of the temperature changes? Okay, that also that you should take into consideration when it comes to environment. So this is environment space. And then we have the time complexity. So it's a way of representing the amount of time that is required for the program to run till its completion. Okay. So the graph is quite simple. Okay, for the input that is being given, okay, with less amount of time or maybe minimum amount of time, okay, you are going to get a linear output. Okay, so that should be the objective of data structures. And then we have the space complexity of algorithms. Actually, I want to discuss something about this auxiliary space. Okay, that's the reason this slide was introduced. So, with the case of the algorithm, what you're trying to design, we have like variables, maybe temporary variables or maybe permanent variables. We have constant values, we have temporary values as well, and then we have program instruction, the set of instructions to perform a required task, and then we run it, we execute it as well. So it shouldn't be confused with the space complexity. Okay, this auxiliary space, because auxiliary space is a subpart of space complexity. So in the space complexity, we have auxiliary space as well as the input space. The auxiliary space is actually an imaginary space or predefined space that is added along with the input space. So what you call it to be the space complexity. And then there is memory usage while execution. So while executing or maybe while running the tasks, generally the algorithm tend to use more memory space. Like we have instruction space. So it's actually the amount of space or maybe amount of memory used to save the compiled version of the instruction. When it comes to environmental stack, generally the current variables are pushed into the system stack, which means they can wait for further execution, and then you can make the call to the inside algorithm. We'll take an example, and then you will understand things better. We will have two functions, function A and function B. And if function A calls function B, then all variables of function A will get stored on the stack temporarily, while function B is actually called and executed inside function A. So this is how the functions act. Okay, so if function A is trying to call this function B, the variables will get stored on the stack temporarily, and function B is called and it will be executed inside function. So function A, it's actually an area or maybe a space where function B is being executed. And then we have the data space as well. So data space is nothing but the amount of space which is being used by the variables, okay, or maybe the constants in order to perform a particular task. So this is all about the the memory usage while execution as well. Let me bring to you a very simple differentiation between a static data structure and a dynamic data structure. Of course, you know it pretty well that a static data structure generally, like, everything is being constant, everything is cannot be changed, which means that we have a fixed memory size as well. But in the case of a dynamic data structure, the size can be randomly updated during the runtime, which means that it can be considered efficient with respect to the memory complexity of the data. So static data structure, if you can analyze the benefits, it's offering easy access to elements when you compare it with the dynamic data structure. And unlike the static data structure, dynamic data structures are flexible even. And there are several approaches, how you try to encounter when you try to design an algorithm. You can start with a top-down approach as well. Maybe top-down, okay. You can start from the top and then you can come down to the down, okay. So top-down approach will have identification of major components of the system or program, which is decomposing into the lower level components. Okay, so the larger problem, maybe from the top, it gets subtasks. Okay, for example, let us take in the case, your institution has a president. Okay, so the president, if he wants the university to get accreditation, or maybe if he wants the university to get some good name, he tells it to the dean of the college. So dean, what he does, he distributes the task to the heads of the department. Heads of the department, what he does, he distributes it to the faculty members. Faculty members, what they do, they will tell to the students. So students, they try to participate in some good competitions. They win prizes. They win awards. Okay, so this is how the top-down approach acts. Okay, so it's iterating until the desired level of module complexity is achieved. So we started up with the president and we ended up with the students. Okay. So here we start with the topmost module and incrementally we add modules that counts. And then we have the bottom-up approach. Okay. So whenever you students have a problem, what do? You will discuss this with the faculty members. Faculty members will discuss with the head of the department. Head of the department will discuss with the dean. Dean will discuss with the maybe the rector or maybe the vice rector. Vice rector or maybe the rector discuss it with the president. So this is bottom-up approach. You have a problem, but finally it ends with the president. Okay, so this is a bottom-up approach which starts with designing most basic or primitive component and proceeds it to the higher level components. So starting from very bottom, the operations that provide layer of abstraction are being implemented. Now here we consider a simple algorithm to add two numbers and display the result. Okay. Let us take in the case, we start step 1, start. Step 2, you initialize the three integers a, b and c. Step 3, you define the value a is equal to 1, b equal to 2. Let us take in the case. Okay. And step 4, add values of a and b. Okay, maybe 1 and 3 you add it, maybe it is 4. Okay. Step 5, store the output of step 4 to C. Okay, so 4 you're going to add it with C, and then step 6, print C, and then you go with step 7, which is stop. Okay, so A and B you are adding up and you are storing it as C, and you are going to print the C. Okay, so 1 plus 3 is 4 is printed to C. Okay, and then you stop the program. So this is an algorithm, a very simple algorithm, how you add two numbers and display the result. So when you analyze, several data structures, several abstract data types, and design patterns, the basic idea behind formulating this efficient algorithm depends upon how you try to organize the data. Okay, so it's the organization of data really matters when it comes to different types of operations. Maybe you take in the case of several trees, or maybe graphs, or maybe heaps. It all depends upon the choice of the algorithm and how efficiently you are performing your this algorithm in order to do the task and get the required output. So whenever you talk about data structures, which means that we need not have to worry about the implementation details that is associated with the programming languages, or how the data is being stored in the computer. So here within the design patterns, we have like abstract data types, which are defined only by the operations that are performed on them, and we specify how they are built out of more primitive data types. Okay, so how you are going to extract data from them, and what are the basic checks that you should do to control the processing about algorithms. Okay, here whenever you go for abstraction, you have something called encapsulation. I discussed this in the object oriented programming subject. I hope you remember the concept of encapsulation, which means hiding of data, okay, from the public usage. Okay, which means that the implemental details or maybe the base design details are hidden from the user and protected from the outside access. We discussed about this encapsulation process in object oriented programming. So the same case repeats with the data structures. So this is abstraction. Even if you consider the higher level of abstraction, they are design patterns which describe the design of algorithms rather the design of data structures as well. So you tend to categorize or summarize the concepts. Even we have a general structure for algorithms. We leave the basic details or maybe design details. Okay, so these design concepts can speed up the development of the algorithm. We have like several algorithm structures as well. So that's the reason whenever you come up with any mobile app, this is abstraction where you tend to categorize it, but at the back end it is encapsulation. They are showing you only the relevant information you want to learn. Okay, I told you the example in the object oriented class. Okay, like maybe whenever you are driving the car, whenever you are pressing the accelerator, okay, it increases the speed, but how the car is increasing its speed, you do not know. Similarly, when you are pressing the brake, of course the car stops, but how the mechanism, how the car is being stopped, you need not know, and you need not want to know about it. Okay, so this is encapsulation. And then these are the popular data structures. Okay, so we have some popular data structures in practice. So here we have an array, okay, which is a collection of items stored at contiguous memory locations. So we have to store multiple items of the same type together. Okay, so which means that it's easy to calculate the position of each element by adding an offset to the base value. For example, we have the memory location like 0, 1, 2, 3, 4, 5, 6, and so on. Like U, B, F, D, A, E, C are the memory location. So we allocate to 200, 201, 202, 203, 204, 205, 206, and so on. So which means we are adding an offset to the base value, which is nothing but the memory location of the first element of the array. Okay, so it's actually the name of array. Okay, so it can be U of 0, B of 1, F of 2, okay, D of 3, A of 4, E of 5, and C of 6. So this is how you categorize an array. A of 0, A of 1, A of 2, A of 3, and so on. And then you have a linked list. So just like arrays, you have a linked list, which is a linear data structure. So linked list elements are not stored at a contiguous location, which means that the elements are linked using pointers. For example, you have like A, B, C, and D. Okay, A is actually where you have the head, okay, the data, and it points it to the next B. Okay, so this B is the head now, and it points to C. Okay, C becomes head now, and then it points to D. So whenever the point is at one particular location, so this is the current head, and it points it to D, and this D points it to none. So here you can see that the elements are linked using pointers. When you have the stack, which is a linear data structure, we have, I've already told you the example of a bottle. Okay, we have first in first out, or maybe last in first out. Okay, FILO, FILO, which is first in last out, or maybe last in first out. So you're maybe storing maybe like in a bottle. Okay, 0, 1, 2, 3, 4, 5, 6, 9, 2 is considered to be top. So it comes out first, and 5 comes out last. So this is last first. So here are the basic operations which are performed in the task. We have push, we have pop, peek or top, and then is empty. Push means we are going to add an item to the stack. We are going to push it, and if the stack is full, then you will have an overflow. Okay, maybe you are filling the bottle. Up to some amount of time, you can fill the bottle. After that, it overflows. Okay. Similarly, pop. Suppose you are having a bottle full of biscuits, you can remove an item. Okay, by turning it diagonally. Okay, so the items are popped in the reverse order in which they are pushed. So the first item which is being pushed is the last item that has to be removed. Okay, and if the stack is empty, which means you have a underflow condition. And then you have peek or top, so which returns the top element of the stack. Okay. And then is empty, it is going to return true if the stack is empty, and it is going to return false if the stack is full. Okay, so this is empty. And then we have a queue. So just like stack, we have a queue, which is a linear structure where it is going to follow the order in which the operations are being performed. So here in the order, we have first in, first out. Okay, so that's a good example where there is a queue of consumers where the consumer that came first is served first. Okay, so this is a queue. So like maybe like a movie theater. Let us take in the case. So one who comes first to book the ticket maybe gets first to get inside the theater. Okay, so this is first in, first out, and there is difference between a stack and a queue. In a stack, we remove the item that is most recently added, but in a queue, we remove the item that is recently remove the item the least recently added. Okay. So this is a queue. This is 0, 1, 2, 3, 4, 5. This is front 7, 2, 6, 9, 1. This is the front, and this is the random. And then there are several basic operations that are performed in a queue. So just like a stack, there are some basic operations that are performed in a queue. So we have in queue, we have DQ, and then we have front, and then we have ram. Okay, so in queue is going to add an item to the queue. Okay, so if the queue is full, which means we have a overflow condition, but if we have DQ, it is going to remove an item from the queue. Okay, in queue means you're going to add an item to the queue. Okay, and if the queue is full, it is overflow condition. DQ means you are going to remove an item from the queue, so which means that the item are popped in the same order in which they are pushed, and if the queue is empty, you have a underflow condition. So just like stack, you have the feature, but the only difference is that you have first in first out with queue, but last in first out with stack. And then you have front as well as rear. Front means get the front item from the queue, and rear means get the last item from the queue. Okay, so this is all about the basic operations that are performed in the queue. Actually, I think Sanjar has left. Actually, Sanjar, what he was trying to ask is the short video. Okay, actually, uh, you can tell him that maybe he can join in the Google Classroom. Maybe I'll share the syllabus, I'll share the materials, and inside the materials you will have the video. You'll have the video link. Okay, so I think this was what Sanjar was asking in the Telegram group. So what we'll do? Yeah, you are trying to share something.
Okay, one thing I want to ask.
Yeah, tell me.
At the beginning of the lesson, you told us to make a project, yeah?
Yeah.
And what time is the deadline?
Before the end of the course. Before the end of this particular subject. But I would rather
End
request.
of this
Yeah.
semester?
Yeah. Before the end of this course.
Okay.
Whenever they ask for the internal
Okay.
marks. Okay. So you should complete it before
Okay.
the deadline. But don't wait till the deadline. That's my humble suggestion. Don't wait till the deadline. You can start working right from now. And open-ended
Okay.
project, I told you, it is open-ended, which means it's an application-oriented. So I have shared you the syllabus. You can choose whatever topic you want to, but make sure you have some objective. You have some plan. What are the tools? What are the specifications that are needed? How you process the input and how you get the results. And you should share me the maybe the coding and the results also. But it should be an application oriented project. Don't simply do it from the internet, but do something out of your own.
Mm-hmm. I will try to make e-commerce.
Okay, right. So this is what I'm trying to tell you. Okay, so please do complete it on time.
Okay.
Here comes binary tree, where you have we have already discussed about like arrays. We have already discussed about linked list. We have already discussed about stacks and queues. But a binary tree is something different. Okay, they are considered to be hierarchical data structure, and in binary tree we have a tree data structure in which each node has at most two children. For example, let us take in the case your parent has a son or maybe a daughter. Okay, maybe a left child or maybe a right child. It is being implemented mainly using links. Okay, so here a binary tree we represent it by a pointer to the topmost node in the tree, and if this tree is empty, then the value of the root is null. Okay, so here in the binary tree we have a data, we have a pointer to the left child, and we have a pointer to the right child as well. So in the tree we have like sub parts. Okay, and we have some information for connecting to the left as well as the right child as well. Okay. So this is all about the binary tree, and then we have a binary search tree as well, which is a binary tree with some additional properties. So there is some difference between a binary tree and a binary search tree. So here the left subtree of a node contains only nodes with keys less than the node's key, and the right subtree of the node contains only nodes with keys greater than the node's key. Okay, the first subtree, the left subtree will have nodes with keys less than the node's key, but with the right subtree it will have keys greater than the node's key. Here when you define the left subtree and the right subtree, it should be a part of the binary search tree. So whenever you are searching for any item, let us take in the case it is between maybe 250, let us take in the case, it will check for less than 250, and the second case it will check for greater than 250. Okay, so like two different probabilities we are going to check, and then you are going to come to a conclusion. So this is very much useful whenever you take into consideration of the complex algorithms or maybe complex programs that you try to develop. So this is all about the binary search tree, and then we have a heap. Okay, so heap is a special tree-based data structure in which the tree is actually a complete binary tree. We have maximum heap and then minimum heap as well. So here the maximum heap, the key which is present at the root node must be greatest among the keys which is present for all of its children. Okay. So we have a maximum heap as well as minimum heap. So here the key which is present at the root node must be the greatest. Okay, and the same property should be the true for all the subtrees. Okay, so let us take in the case this is similar to a parent-child relationship as well. So if the parent is of that character, maybe the child would have that at most of the characters. So that should be the maximum heap. And then the minimum heap is that the key which is present at the root node must be the minimum among the keys present at all of its children. So which means the same property has to be true for all the subtrees in the binary. So this is heap, maximum heap, and then minimum heap. We have an example for minimum heap as well as maximum heap. So similarly, if you see this one 10, 15, 30, we have 40, 50, 100, 40. So this is the minimum heap. Okay, and this is the maximum heap. Okay, so this is how the heaps takes place, like how much distance it takes place, how we are going to calculate the distance between its nodes, and how we are going to reduce the time space of the function. And then we have a hashing data structure as well, which is a very important data structure. So hashing data structure, we have a hash function. It is going to map a given value with a particular key for a fast access of emails. Okay. So here a hash function h of x which maps the value x at the index x modulus 10 in an array. Okay. So here we have the list of values 11, 12, 13, 14, 15. Okay. So it will be stored at the positions 1, 2, 3, 4, 5 in the array. Okay. So or maybe it can be stored in the hash table correspondingly. Okay. So this is hash data structure where we tend to store the values in the respective locations. This is the hashing data structure. Okay, so we have the list 11, 12, 13, 14, 15. So it is represented as h of x, which is x modulus 10. Okay, so it can be 11 modulus 10 or 12 modulus 10 or maybe 13 modulus 10 or maybe 14 modulus 10 or maybe 15 modulus 10, which is stored in the locations 5, 4, 3, 2, 1 and so on. So this is how it is being used. This is hashing data structure. And then we have a set of matrices. So matrix, it represents the collection of numbers arranged in an order of rows and columns, and it is necessary to enclose the element of the matrix in parentheses or brackets. So we have a matrix with 9 elements 1, 2, 3, 4, 5, 6, 7, 8, 9. So similarly like row 1, row 2, row 3. Okay, column 1, column 2, column 3. Like A of 0, A of 1, A of 1. Okay, B of 0, B of 1, B of 1. C of 0, C of 1, C of 1. So you can designate it whatever way you want to, and it is going to represent a collection of numbers in set of rows or maybe columns. And finally a trie. It's a efficient information retrieval data structure, and using trie, search complexities can be brought into a fixed key length as well. And if we stored keys in the binary search tree, it's a well balanced BST will definitely will need time that is proportional to the m multiplied by log n. Okay, m is actually the maximum length of the string, and n is actually the number of keys in the tree. So it is a well balanced binary search tree will need time proportional to m multiplied by log n. Okay. And using try, we can search the key in the order of m time. Okay. So it's a efficient retrieval data structure. So this is the thing. Root, we have G, E, E, and within E we have K, R, and Z. Within K we have S, T, and within S it goes on. So this is a so we have some independent works, graphs, graph terminology, implementing graphs, and then relations between graphs as well. And then we'll discuss about shortest paths as well. You can discuss about these topics. You can come up with a minimum of 10 slides about an introduction, about the description about the topics, and you can give some relevant examples with some diagrams as well.